So, this is a thermometer, and everybody knows it measures temperature. The clock, and you know that it measures time. And in both situations, what you see is what you get. The nature of this kind of measurement is quite direct. You can trust the clock and the thermometer quite well. Of course, respected the fact that they have been well calibrated and there is no functional defect. But how can you measure the knowledge level of a physician or the competence of a physician? In this situation, the nature of the measurement is much more indirect. And in this regard, we have to say that scoring students is a quite controversial issue. Lord, not God, but one of the creators of item response theory has already said that religion, politics, and formula scoring are areas where two informed people often hold opposing ideas with great assurance. So, we have two histograms from the same progress test. But why do they differ? In the left side, we have a histogram of theta scores, which are produced by item response theory, and in the right side, the raw score, a histogram with the total number of correct answers, which is produced by a classical test theory software. You can see that the shapes of the histograms are different. You can also notice that the numbers of the scores are different. So if you take a closer look at the theta scores, you will see negative marks, and in total score of the right side, only an ascending number without negative scores at all. So in the left side, we can see that, well, it seems like a standardized distribution. Yes, it's true. It's like a z-score or a t-score, with the 0 being the mean and minus or plus 1 being the standard deviation. If it helps you, this is a good way to explain it for now, but perhaps not the entire truth. Now we are going for the entire truth. Should these calculations have the same value on a test? We have here 4 different math problems, and we can see that the more to the right, the more complex the item gets, the question gets. Now imagine this other one. It's even more difficult. So if you compare to the first problem, to the first question, is it really fair, or is it really appropriate to give the same value on a test for these so different calculations? Well, if you think it is the case, if you think that it's really correct to give the same value for each one of those calculations, be my guest, and you can already stop this video. But if you think that no, that we should account differently each one of these different problems, then I invite you to follow me further. Imagine that we have here a seesaw. In one side we have the person, and in the other side we have the question, we have the test. So what's the probability that the person is better, or may I say stronger, than the complexity of the task? And what is the probability that the person will win this seesaw battle? There are formulas to estimate that battle, but I will not bother you with that. I mean, these formulas are too complex. But, you know, we can translate that into plain words. This item response theory thing is so special because it takes into account the difficulty of each item to calculate the examinee's grades. So if we call it a theory, it's actually not making enough justice to what it is. Because actually, when we call item response theory, we are referring to a set of different probabilistic models that are able to establish a relationship between the probability of success of the student on each question, which we call item, with the degree of knowledge of these test takers. So, classical test theory already told us that any observed score is the sum of the true score or the error. But they say that in variance terms. But anyway, I'll not bother you with math. I promised you that. What item response theory does is to rename the elements of this equation a little bit, calling the observed score the tau, or the observed behavior, and the true score, they call it theta. So what item response theory tries to do is to find that true score, to find that theta, while establishing the error as well. So we never really know the true score. Item response theory is not able to truly know, but it's able to give a more precise estimate of this true score. So despite we never know the true score, we get almost there. It's the closest that we can get when we use item response theory. So that's why they also call it the true score theory. So these models use the notion of a non-observed variable. We call these non-observed variables a latent variable. In our case, in medical schools, for example, this latent variable would be medical knowledge. This would be the construct that we want to measure, or even better, application of medical knowledge. And then we try to make sense of the student's level of this medical knowledge or application of medical knowledge level from these observed behaviors, from these raw scores. So we try to estimate the theta by looking at tau. So how does item response theory does that? What's the secret? Will I be able to understand it? So imagine this matrix of hypothetical tests. In the rows, in the lines, you have the students. In the columns, you have the items. And the cells of this matrix, you have zeros and ones. Zeros for incorrect, 1 for correct. If we rearrange this data, we have a triangle-shaped format. So this is a way to, how can I say that, mirror the axis of the items with the axis of the students, of the test takers. So you actually can see that one mirrors the other. The axes are kind of a mirror of each other. And this is not, of course, seen in all tests. Of course, in most tests, you have some blank dots, some zeros where you shouldn't have. You have some ones where you also shouldn't have. And what the psychometric software does is to try to achieve that triangular shape as much as possible. To do what? This is the biggest secret of item response theory. The secret to understand it is that the software is able to model the data in order to put both items and students in the same scale, in the same spectrum, which we call the theta scale or the theta spectrum. And then we can make the probabilistic estimation of who will win the seesaw battle. And here you have items in blue and persons in black. And you can see that they are put in the same scale. That's what it does. You can take a look at this graph above. You have Johnny, you have item 7, and here you have Johnny in the right side when compared to item 7. Here we can say that the probability of success that Johnny has in item 7 is above 50%. And the farthest he goes to the right, the higher will be this probability. In the lower graph, Johnny is in the left side now, so the probability of success in item 8 will be below 50%. And the more Joni goes to the left, the lower will be this probability. What if Joni and a hypothetical item 9 are exactly on the same place of that theta scale? Then we say that the probability is estimated to be exactly 50%. So for each one of the items of any given test, item response theory analysis will draw this graph, the item characteristic curve, where it displays graphically the logistic regression that is done for each one of the items. And here you have the discrimination parameter, A, which is the ability to distinguish between good and bad students that the item has, which is a very good indication of the validity of the item, perhaps the best one. B is the difficulty, so the more to the left, the easier is the item, the more to the right, the more difficult is the item. And on letter C, we have the probability of success due to guessing. Of course, this is also not known, it's only estimated. But this estimation can also bring some interesting information, despite being only an estimation. For example, in this item we can see that there is clearly some problem. This item was easy. This item was very non-discriminative, because the probability of success in this item didn't change too much across the theta spectrum, and it had a pretty high level of success due to guessing, at least in this estimation, in this mathematical modeling. So you may ask now, isn't it too complicated? Why should I use it? Are there any practical advantages? Yes, there are. The first advantage is that we can estimate the degree of reliability and error for all spectrum of theta. In classical test theory, reliability and error are only calculated for the test as a whole. And with item response theory, you can do that in a graphical, very sophisticated manner. So for example, in item response theory here, there is this calculation for a progress test. You can compare the Cronbach's alpha of 0.8, which is produced by classical test theory, and you can see that for top students, for the best students, the reliability, which we also call precision, is even above 0.9. But for the lowest achieving students, it was much lower. Still above 0.5, which is good, but anyway, much lower than for the top students. The second advantage is that we can use this mathematical modeling to estimate and control the guessing. You can actually have a much better control for guessing with item response theory, and avoid that the student will benefit unfairly from guessing. The third advantage is that when certain assumptions are met, and this is a statistical part, I will not bother you with that, but when these assumptions are met, item parameters, not only discrimination and difficulty, but also the C, the guessing, they will be relatively invariant. They will be relatively stable. So when we have different formats or different forms of a test that are measuring the same construct, the same thing, for example, medical knowledge, or even better, application of it, we can equate these different forms in order to put them in the same scale. We can put different formats of tests in the same theta scale, and then we can compare results from different tests, respected the fact that we will need to have a set of around 20% of the items common between these two tests. This we call the anchor test design. So if we have some items in common, and then we have the majority of the tests different, despite that we use this common part of the test to estimate the parts that are not common, to estimate and standardize the difficulties of the parts that are not common. And that's why we can compare the tests in an appropriate manner. With test equating, the students that need a receipt for any justified reason and will do a different form of the test can have their scores compared to students who did the first version, who did the original test. Test equating then, because of this, also helps in accurate standard setting, not only when we need to do a receipt, but when we need to use different versions because of removal or replacement of contents that are too local, for example, in an international version of the test. Just to give a more clear example of what I mean, here we have the cut score of the original test. Because we calibrate the items together from both forms, we can estimate the equivalent of these original scores in theta scores, and then we can use this theta score equivalent of the first norm, of the norm of the original test, as the equivalent in raw answers, for example, or formula scores in the second version. So we can do this conversion table and then ensure that the most accurate strictness level is kept, is maintained. Another advantage, item response theory has higher predictive validity. And this means that the scores generated by item response theory are much more meaningful because they really reflect much better the future performance of test takers in a similar exam or at accomplishment landmarks. For example, I did this study which I tried to predict who would be approved at any given medical residency in Brazil as a function of progress test scores. Only theta scores produced by the 3-parameter logistic model, which accounts for guessing, was able to predict correctly 84% of the results. All the other ones were predicting less than 50%, so they were not useful and they were also not significant, not meaningful at all. So this is a clear superiority of IRT in terms of predictive validity. But anyway, there are disadvantages. There are some pitfalls that have to be avoided. If theta scores are somehow reported to students, not only for internal quality assurance purposes or standard setting calculation of cut scores, you have to be prepared to understand and explain a few points. For example, why certain things can happen, like different theta scores despite the same raw scores. What are theta scores anyway? What about the residues, the difference between observed and modeled data? So it is necessary to educate the staffs, the students, and the relatives not only one time, but many times. It is also important to notice that international testing has been regulated somehow, at least in a soft way, by standards and guidelines that clearly recommend that we take into account and try to discard or eliminate the influence of construct irrelevant sources of variance, for example, language and cultural aspects. Item response theory is able to help us comply to these standards and guidelines by doing what we call differential item functioning. This is not very difficult to understand, but imagine that you have two students from different ethnical or linguistic backgrounds. So they are separated by, for example, being a foreigner or a native, and then they have the same theta scores. But at a given item that was translated, for example, there's a significantly difference between the probability of their success in that particular item, despite the fact that they have the same theta level. So this is something that calls our attention, that perhaps in that item something else besides medical knowledge is being measured. So we can take that into account to enhance fairness and validity for international students. Thank you very much. I hope you have enjoyed. I hope this was not very boring or not very complicated. But if you still have doubts, please don't hesitate to get into contact. Write me and place your question. Thank you very much.